Hello and welcome. Today I'm going to talk about Newton's universal theory of gravitation. I'm going to start with some general ideas about what fundamental forces are, also called interactions, and then talk about gravity, which is one of these fundamental interactions. So our topic is universal gravitation. Universal means it's the laws that describe gravity are universal. They're valid everywhere. So far, you're already familiar with things like acceleration due to gravity. G, right? Now it's 9.8 meters per second square. Is it always this number everywhere in the world? Not exactly. There are variations to it. Maybe in your problems, you didn't have to worry about that much. But if you climb up a mountain or if you move from Houston to Alaska, this number will change. So it is not that universal, especially once you leave Earth. You don't have this number anymore. And you may have a weightless environment, like in outer space. Does it mean there is no gravitation? See, that's the question. Now, what we're going to find out is not specific to Earth or some other planet. It's everywhere. So this is very specific, but we're going to end up with a universal theory of gravitation. This is due to Isaac Newton from 1600s. Okay, it's not a new theory, but it works so well, you can go to the moon with it without any problem. This is the first successful theory of gravity. It had its limitations, and another theory was developed by Albert Einstein about 100 years ago. Albert Einstein, this is part of his theory of relativity, the general theory. So 1915 and 1916 with observational proof, and maybe in 2 years. So that is gravity 2.0. Gravity updated. All right, now we're not going to go into this, but focus on Newton's universal gravitation. This is one of the four fundamental interactions in the nature we know. So 4 basic forces, also called interactions. Now, force in this context is not the force we dealt with when we did the pulleys and ropes and then objects you push and pull. Those were contact forces. Now we're talking about fundamental interactions which happen through what we call fields. It's an action at a distance, okay? And gravity is one of them, like Earth is attracted by the sun, which are not in physical contact. So there is a force between them, although there's so much space. Now, what other forces do we know which act at a distance? 2 magnets. If you put them side by side or bring it to your fridge, you'll see that there's a force without any physical contact. So such forces are elementary interactions. And there are only 4 of them. Only 4 of them. Gravity is the first one. Gravitation. The second one is electromagnetic interaction. Electromagnetic forces, electricity, and magnetism. Now the third one and the fourth, these we don't really experience in our daily lives directly. And it took some time for people to figure out what they are. Now these two are long range forces. Long range, pretty much from here, 0, all the way to infinity. You know, of course they get weak over distances, but in principle, there is no limitation to how far they extend. All right. But the other two, number 3 and 4, you see them only inside the atom. The building blocks of matter, atoms come together to make molecules, but at that level, you're already in the realm of electromagnetic forces. But go deeper, inside an atom, for instance. What keeps the protons together? Now, gravitation is the force of attraction between objects that have mass. Electromagnetic forces, electrostatic forces, for instance, is the force between electric charges. Now, these charges come in two flavors. They're either positive or negative, If you have like charges, they repel each other. Opposite charges attract each other. So it's two ways, whereas gravitation is always attractive. That's why over large distances, you have equal number of positive and negative charges, so they neutralize each other. Therefore, you don't have any electromagnetic interaction between, let's say, Jupiter and Saturn. As far as we know, there's no such interaction. At that level, the forces are really weakened out. But gravity is always there. Although the weakest force, I'm going to come back to this point, but let me just make a note here. The weakest of all four forces, but since it's only additive, one by one, drop by drop, you end up with enormous forces. That's why it's the only dominant force in the universe. The force that keeps the planets, solar systems, and galaxies together is gravitation. So electromagnetic force is the next strong in that range, but still it's not the strongest. Now think about an atom, let's say hydrogen or helium atom, let's say helium atom, which has 2 protons in its nucleus, and then you have 2 electrons. Okay, this picture is not really, doesn't make sense. Let's just say there's electrons around. We're not going to go into that now, but look at the nucleus here. 2 protons together, 2 positive charges. How do they stick? They should be repelling each other, which they do. But when they are so close to each other, there is this new force kicks in, which we call the strong nuclear force. The strong nuclear, or just strong force, that's also common. Strong nuclear force. This is the force that keeps the protons together. Not only protons, but they're also neutrons. Now, these are 0 charge particles, but they still stick together with the help of this strong nuclear force. And if you're wondering why do we have that force in the first place, well, protons and neutrons are not the smallest particles you can imagine. They themselves are made of smaller particles, which are called quarks. Okay, so there are 3 quarks that are together, which make up a a proton. And there are also 3 quarks, different ones, or different combination, let's say, that make a neutron. But what happens is those quarks are attracted to each other with a force that looks like a spring. There's another one here, another one there, okay? So this is actually a proton, let's say. And when you have another set of 3 quarks, they're also, the reason these forces are represented by springs is when you stretch a spring, the force between the 2 objects increase, as opposed to the force between 2 electrical charges. When you separate them, the force goes down. Same with gravity. I mean, take moon farther apart from Earth, the force between them goes down. But in the case of the strong nuclear force, this force, at least in that range, it increases when you increase the separation. That's why I drew them like springs. Well, just a representation, okay? So if you don't agree with this, and if you really know much about quarks, you're welcome to come up with your own representation, all right? But what happens is these 2 protons should be attracted, so we have now another spring there, okay? So that's why they stick together, okay? That's a strong nuclear force. And there's also the weak nuclear force, or the weak interaction. And this is responsible for radiation or radioactivity in atoms. Radioactivity. Okay, so let's leave it there and focus on gravity. Gravity is the weakest of all. And it took a long time before people discovered what gravity is, or there's such thing as gravity. Of course, everybody knew that objects fell down when dropped, although they had the wrong ideas. The Greeks, for instance, Aristotle had some ideas. Aristotle and Ptolemy, the ancient Greek philosophers, but they had the wrong idea. They believed that, for instance, heavier objects would fall faster. They would accelerate with a greater acceleration. This is wrong. I mean, due to Galileo and Newton, we know that this is not correct. And experimentally, this is also Galileo, a fact that objects fall with the same acceleration. But it was Newton who connected this idea to the motion of heavenly bodies. And that's where the success is. So the first consistent and successful theory of gravitation, why objects fall, is due to Isaac Newton. So he said that objects with mass attract each other. There is a force on each object. And from our study of Newton's laws, the 3 laws, we know how to relate the force to acceleration. And mass is a measure of how difficult it is to accelerate an object. This is called inertial mass, okay? So even if you have just one mass and a force acting on it, you have F equals ma, you understand it. But there's also the 3rd law. If 2 objects are interacting, like this object is pushing against the other object, then the 3rd law, 2 objects in contact, object A and B. Now there's a force that A exerts on B. Let's call it F, or FAB, means A pushes B. In return, B pushes A. So this force will be on A because of B. You will never have F by itself. It's going to have its counterpart, These are called the action-reaction pair. So FBA is object B pushing A, okay? Pushing, pulling, in the case of gravity, it's going to be an attraction, right? So two forces, opposite in direction, but equal in magnitude. That's what the third law is about. Now, when Newton was formulating this, I'm not sure how exactly it went, but this one, the third one, is a perfect example for gravity he was coming up with. So here we have the sun, here we have the earth. Sun will attract earth toward itself. In a similar fashion, earth will attract sun towards the earth. These two forces will be the same in magnitude, but opposite in direction. So F sun pulling earth toward itself is equal to negative FES, the earth attracting the sun. Now, no matter how different the masses are, the force in magnitude will be the same. They will be the same. So the absolute value of FES will be equal to the magnitude, not absolute, magnitude of FSE. Okay, I mean, this pen is attracted by earth, which we called weight before in our previous classes. But in return, the pen pulls the earth in the opposite direction with the same force. Okay, very important point. So this is Newton's third law. Newton's third law. So his formula for universal gravitation had to reflect this fact. If you change the masses, the force had to remain the same. Okay, now that's very important. I mean, algebraically, if you have two numbers, in this case, we're talking about masses, let's call it MA and MB. Okay, like if you multiply them, yeah, you can change the order, right? This will be equal to MB times MA. But MA, let's say you divide them, MA over MB is not equal to MB over MA unless, you know, they're both equal to 1 or something, or the same number. If the masses are equal, the ratio will be 1. But just trying to say that the formula that has gravity due to both masses should be symmetrical in terms of A and B. You should be able to commute the masses and still get the same answer. So gravity as a force should be proportional to the masses, because if you add masses together, you create larger stars and galaxies. The force that you obtain also has to be greater. And there's no reason if I double the mass, the force should quadruple or something crazy like that. So we assume, that's a very good one, that the force is linear in masses. Okay, so let's take this multiplication and then use it as our starting point for the formula. Two objects, their masses are MA and MB, and we multiply them to obtain the force between them. Okay, FAB equal to FBA. I'm just going to call it F gravity. F gravity. Now, these two objects don't touch each other. They are at a distance. So the distance between them has to also play a role. So if you change the distance, the force should change as well. All right, so how? Well, if you increase the distance, the force should decrease. So we should have a dependence on R, and we should write R So let's draw a picture here. This is A, and this is B. The force should decrease. So I need to put R, the distance between them, in the denominator. So that's one of the choices, right? When you put R in the denominator, you increase the distance, the force goes down. But it's not the only option. Is it R or R squared or R cubed? All right, so which one is it? Is it 1 over R, 1 over R squared, 1 over R cubed, or 1 over R 2.3, okay? Well, in nature, you don't really see these that often, so don't worry about these. But one of these, okay, should be the choice. And there are physical and mathematical reasons for why this one is the one, okay, 1 over R squared. There are actually experiments done. Now, although this force is so weak, it's so weak that, you know, let's say these are two objects, I'm holding them together, I don't feel any force at all. It's negligible. Imagine these were magnets. You would definitely feel the attraction, right? I mean, the electromagnetic forces are, what, 10 to the power 33, I think, that many times stronger than gravitation. You don't feel it, so it's so weak. So how can you even make an experiment, you know, and then find out what the dependence on R is? Well, it was done in a long time ago, 300 years ago by Cavendish. Actually, a very smart experiment by Cavendish. So it's experimentally proven that it is 1 over R squared. And also Newton had other reasons. I mean, this theory had to agree with the motion of the planets and all. And Johannes Kepler already had very good data. Okay, and then there are other reasons too, all right? I mean, I don't know all the details. I've never read the Principia, Newton's famous book. So if you're really curious, read this book and find out what reasons he had, but it is R squared. And this 1 over R squared, the inverse square relationship, also happens with electromagnetic forces. You just replace the masses with charges and then it works like a charm. Now here's a problem though. Like I was saying, two forces are really, really small, really weak forces. So if these were two masses that you can easily find in your labs, physics lab, let's say 1 kilogram. MA is 1 kilogram, and then MB is also 1 kilogram, and the separation between them is 1 meter. Okay, by the way, when I write the separation between the two masses, I pick a point inside the object, okay? Like in this case over here on the left, I had these two spheres touching each other, okay? If I were measuring the distance from one surface to the other surface, R would be 0, right? 1 over 0, it's not determined, so infinite. So you don't have that, okay? So these points are inside the objects. In practical calculations for planets and all that, you know, it doesn't hurt if you just consider those particles to be point particles, because like the Earth-Sun distance is 149 million kilometers. So, I mean, Earth's radius is really small compared to that. Anyway, so going back to this, some mass you can find in the lab, okay? 1 kilogram here, 1 kilogram there. Just hold them a meter apart. So 1 times 1 divided by 1 squared, you get 1. Is that 1 Newton? No, it's not. It's not 1 Newton. So this formula now is not complete. We need a constant here, which would scale this quantity down to a reasonable, but not reasonable, to an experimental real value, okay? The real value is much smaller than 1 Newton, much, much smaller. So that's number one reason why we need a constant here that would multiply MA, MB over R squared. And there's another reason why we have to consider a proportionality constant there, and that has to do with the units. So the dimension, see, we have kilograms here. Another kilograms makes kilogram squared. Kilogram squared, that's a square, sorry. My pen doesn't go all the way. That's a square. Let me just erase this. It's a kilogram times kilograms, so kilogram squared. Denominator, we have meters squared. So kilogram squared over meter squared. And on the left-hand side, we'll have newtons. Well, we know what newtons is in, in the standard system. Just remember Newton's second law, F equals ma. So 1 Newton is nothing but 1 kilogram. Acceleration is meters per second. So 1 kilogram meters per second square. Acceleration is meters per second square. So 1 kilogram meters per second square. So on the left, okay, there is kilograms, but not kilograms squared. It's only kilograms meters over second square. Here, meters in the denominator, here's meters in the numerator. Here I have second square, I don't see any seconds at all, okay? So there's something going on there, okay? That's the number two reason for a constant there, okay? So that's what we're gonna call the universal constant of gravitation. Universal gravitational constant. That's Newton's constant. And Mr. Cavendish actually did measure this, okay, which is really close to the value we know today. A very small number. Actually, Cavendish calculated, I think it was the mass of the Earth. So in an indirect way, here's what he did. So he used some masses. Okay, let me switch to circles here. So he took, well, this experiment can be done in different ways, okay? And the modern ones are done with laser lights and all that. But basically, there's a YouTube video. Maybe I should find that and add this in the comments. Somebody did this experiment with the tools of the time. Cavendish, early 1700s, I believe. So think of it like this. You have two masses attached to these really long rods. And on the other side of the rod, maybe you have the same mass or similar masses like this, and then like that. And these are suspended. There's a system here. Okay, I think they call it torsion balance. So it's like you have a wire and you twist it and it wants to go back to its original shape. Okay, so it gives it a restoring force, let's say. Okay, the details are not that important, really. I mean, you can find it about this online. You can watch videos if you like. But Cavendish did this experiment. Obviously, these will be attracted to each other, right? That's why he's bothering with these masses. So this will be attracted to that, and this will be attracted to that. Well, this mass is attracted to this and that as well, of course, but they're farther away. That's why he uses long rods. He is mostly worried about this part. Similarly, you'll have an attraction between the two masses here. So he did this and then found out what the constant is, or he found the mass of the Earth, and then from that we know what the constant, universal gravitational constant is, okay? A very small number. Its value is 6.67 times 10 to the negative 11. All right, now the unit thing, okay? So you got to have newtons on the left-hand side. There's no newtons here yet, so you put N here for newtons. You got to get rid of the meter squared, so you put meter squared here, divided by kilogram squared. Okay, so either you use this unit, which is fine, or you plug in kilogram meters per second square for newtons. And if you do that, you'll end up with, okay, let me try meters times meter squared. You'll have meter cubed and kilogram squared, kilograms. So this will be kilograms here. And then second squared in the denominator. Or this, if I did it correctly. Okay, I think this is more common. Not sure. But that's the unit, all right? So this is the same everywhere in the universe. At least we accept it that way. You know, maybe 20 years from today, someone will come up with gravity 3.0 and then show us that you don't have this, okay? But this is Newton's theory. G is the same everywhere, unlike the little g, okay? Little g is this number only in your physics lab or in your exams, okay? In real life, it varies. From the variation of the little g, actually, you can determine if you have oil, right? I mean, right now, maybe there are planes over the Gulf of Mexico flying and measuring the variations in G and see where you have a certain type of rock or, you know, some salt, you know, there are huge chunks of salt under the ocean. So that varies, okay? You climb up a mountain or you go to a different place on Earth. Earth is not a perfect sphere, okay? Earth is wider on the equator and shorter, the radius changes in the poles. So if you go north, actually you're getting closer to the center of the Earth. So that's another reason why G should change. We'll see those in a minute, or maybe in the next video. But this G, the capital G, the universal constant, no, it doesn't change. The same everywhere. You could be in outer space, really far from any nearby star or planet or anything, okay? Weightless environment, this G is still there, and the force between two marbles that you're holding in your hand will be the same when you do the same thing on Earth, okay? That's why we call it universal, all right? Universal gravitation. So that's the formula, okay? G times ma times mb over r squared. And for now, just think of r as a distance between the centers of two objects, okay? If the mass distribution of the object is not uniform, it doesn't have to be the center. You already know by now how to calculate center of mass, okay? So take the center of mass, and that could be a center of gravity, okay? You wouldn't have a problem with that reasoning. And mass, because it leads to gravity with this formula, mass in this context is also called gravitational mass. Remember in the Newton's second law here, mass was a measure of how difficult it was to accelerate an object. All right, so mass was F over A. So this is the inertial mass here. Inertial mass. You know inertia, right? From Newton's first law and Galileo's considerations. An object will continue to move along a straight path with constant speed unless there's a force acting on it. Once you have force, it won't be a constant velocity anymore. But say if you wanted to change the direction of the object would resist to that change in the motion. That's what inertia is, roughly, right? But that's inertial mass. has to do with acceleration. This mass is called gravitational mass. Gravitational mass. Are these two the same? Okay, that's a valid question. In Newton's theory, there is no reason why they should be different. But in general, this didn't stop physicists from considering possibilities, and also experimental physicists, you know. And so far, we haven't found any difference between the two, as far as I know. I think these are called Eötvös experiments. A Hungarian physicist, I think he was famous for, I'm not sure about the spelling, but let's say Eötvös. So he did experiments in, I forgot the date, but this experiment has been repeated many times. High-tech equipment, okay? And they always found the same answer. So far, we don't know if they're not the same. All right, so just keep in mind, two ways of defining mass. This is now the gravitational mass. Okay, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Now, what about those, okay, these kilogram, what about, well, let's find something, billiard balls. All right, you have a, let's say, pool table, and then you have a billiard ball here, another one here, another one there, okay? So let's find the force on this one due to the other two. Now it's a bird's eye view, okay? Of course there's gravity, Earth is pulling all three. I'm not thinking about that, I'm thinking about the force between these three only. In particular, what is the force on this one due to the other two, okay? So let me just show you what I'm talking about here. Now, this vector represents the attraction of this billiard ball on this. Similarly, this one will attract that, another arrow for that. So this ball will be attracted up this way by this one. Similarly, the one in the corner will attract this. And then these two will attract each other too. Okay, but I want to focus on the force on this ball, and I want to come up with a number. How many newtons, okay? So let me just Google the masses of billiard balls and the size of a standard pool table. Let me come up with some numbers. And in the second video, I'm gonna show you how to solve the simple problem and then maybe move on to more complex problems. Okay, so this is our introduction to gravity, Newton's theory of gravity. Supposedly, he was watching this apple fall from a tree, and then he realized that that's what happens when the moon goes around the Earth. Moon is in constant free fall around the Earth, not towards Earth, but in an orbit around the Earth. So that's when I said, aha. Okay, let me stop here.